Yeah, g'day, it's Charlie ZL2CTM. Well, I just want to do a quick video today just to provide with an update on some experiments I'm doing with the amplifier. At the moment I'm sort of quite happy with that. That's putting out just under 6 watts, so it's 5.87 watts, which is good. That's exactly where I'd like it to be, or in other words just slightly larger than 5 watts, so I'm more than happy with that. So let's just quickly go through what I did. Right or wrong, and we'll go from there. So what we're seeing here is a two-stage amplifier. I took some bit of inspiration from Eric Sear's ZL2BMI's amplifier they did for his double sideband rig, and decided just to elect to go for a two-stage approach to see where I would actually get to. So I'll talk to this more so in terms of what I did for the maths, but this is a junk box 35 watt VHF transistor. I'm actually waiting for some 2SC 1971 transistors to arrive, but they haven't arrived yet, so I was just sort of rummaging around in the junk box and came across this stud mounted VHF, like I say, 30 watt transistor, so I thought I'd use that. And then for the driver, just went for a 2N2219A, which is quite a good driver and works well, certainly in that role. So that's the approach I took. Now this particular device here, the SRF 1001, I could not find. I looked high and low, maybe a little bit of boy's eyes, as my wife would say, and I couldn't really find a data sheet online for that. So I had to apply a couple of assumptions just to get things rolling. So one of the assumptions I took was that it would be about a 300 megahertz or 400 megahertz device FT, but more importantly that the beta DC was going to be something like 170. I don't know if that's right or wrong, but I had to start with something to be able to start working out some of the biasing resistors. And as it turned out, that seems to be quite good, and as an assumption. Anyway, that's what I'm going to talk about here on this. Let me just go and get out the other bit of paper, and we can sort of start to go through the approach I took and that. Now, again, normal sort of caveats. This is not a tutorial. This is just the approach I took, right or wrong. It's working for me. So, like I say, I'm just now documenting that here on the video. So I'm going to start with the right hand side with that the high power device, which I've notionally called the power amp. 12 volts, the low pass filter is coming after that. That's that one sitting over here, and I'll talk to that in another video. That's 50 ohms. So what I want to do for a start, if I wanted to get 5 watts out of this, and my antenna slash low pass filter is 50 ohms, what do I need this transformer here to be to present the correct load for this particular transistor? So using power out equals V peak squared over 2 times RL, I can do a bit of rearranging to make RL the topic, and I can also substitute in VCC for V peak to come up with that expression there. So rearranging, or more the point, plugging in the various values, I've got VCC squared over 2 times 5 watts, my desired output power, comes out to be 14.4 ohms. And what I actually did in this, was I experimenting here, is first I did actually have a transformer where I was transforming that 50 ohms back to be something approximate to 14 ohms. And then what I did as a second experiment, which is what I've actually left in the amplifier, is a 10 turns of bifilar windings on an FT37-43, which gives me an impedance transformation of 4 to 1. So that 50 ohms divided by 4 comes out 12.5, which is pretty close to 14.4. So I elected just to leave it at that, especially because that was a slightly lower value that would kick up, would potentially kick up the power out. Anyway, so I mentioned, right, okay, sorry, stop. Right, these resistors here. First I'm going to work out R2, and my approach was to make R2 We'll determine that using the same approach I've done in the past. The voltage across that device divided by 10 times the base current through it. And then for R1, because I didn't know what the specifications were for this, I elected to start high and then slowly reduce that until I actually got my desired quiescent current of approximately 35 milliamps. I chose 35 milliamps because this is a single sideband radio, so I need to have some linearity in the power amplifier. So I elected to bias this for class AB. So it's not biased at cutoff, it's biased just above cutoff. So, like I say, with a quiescent current of 35 milliamps. So, with that in mind, in terms of determining R2, if I do it like that, you should be able to see both. R2 here, again, that assumption that beta DC is 170 milliamps. I can say then R2 equals 0.7 volts divided by 10 times the base current, which is our the collector current is approximately equal to the emitter current. So therefore, 35 milliamps divided by 170, our beta DC comes out our base current. 10 times that comes out to be 340 ohms. So I just grabbed 330 ohms out of the junk box, and that's that resistor just there. And as I just mentioned, I started high, so I determined what R1 would have been using the same approach, but now having an extra base current going through it. It would be 11 times the current through that device, so it would be 12 minus 0.7 divided by 11 times the base current would give me that resistance. That turned out to be, if I recall, 6.8 K or so. So I started at 10K and then slowly reduced that down until I got my desired 35 milliamps. And as it turned out, I actually didn't write it here, it actually turned out to be, as we can see over here, 3K ohms. So that's what's now currently in circuit. Don't worry about that one, that was just an earlier higher value. So that was all I did for the second stage, or what I've notionally called the power amplifier. For the driver stage, like I said, I went with the 2N2219A here. Just went for a simple single resistor biasing there, and the approach I took was to vary that until I got my desired current going through it, which again I set for 35 milliamps. And by doing that, I came out with a value of 56 k ohms, which is what I kept. Now, let me just talk about this transformer here. I did have a bit of a play around with what I might want to try and use to transform the input impedance here, or just the resistance portion of that, through to the collector to be something like sort of 200 odd ohms for this. In the end, what I decided to do is I just pulled out the junk box of 21 to 7 turn FT37-43 that they already had, and put that in, because with an N of 3 and therefore an impedance transformation of 3 squared, or 9, it was going to be pretty well in the ballpark. And as it turned out, as we'll see when I talk about this in a sec, it turned out to be pretty well on the money with that sort of 5.8 odd watts. And because that's where I wanted to be, I didn't actually decide to vary that in any way. So call it a fluke, call it divine intervention, I'm not sure, but suffice to say, I've just left it as an FT37-43 with 21 turns to 7 on that device here. Now, coming into this device here, we ordinarily want to match what's coming in here to the input resistance of this combination here, impedance, but I'm ignoring the reactive components, I'll just call it Rin. It's coming from the ADE-1, which is a 50 ohm device, so I need to try and work out what this looks like. And because of these capacitors over here, our VCC line from an AC point of view is seen at the same potential as Earth, so therefore looking in here I've got 56k in parallel with whatever this input, or the transistor's input resistance is here. And as we've seen in the past, that input to that particular transistor, or a transistor in that particular configuration, is beta AC times little re. Now there's no big Re, because as we can see here, there is no big RE. If there was a big RE and that had not been bypassed with a capacitor, then I'll be multiplying beta AC brackets little RE plus big RE. So that's why that's missing there. And so the expression is looking in is that beta AC times little RE in parallel with R, which in this particular case R is 56 k ohms. For that particular device, our FT for the 2219A is 300 megahertz. My frequency of operation is 3.7 megahertz notionally. So therefore my beta AC is 300 divided by 3.7, or approximately 81. Little RE, as we've seen in the past, is 26 divided by the emitter current in milliamps, so 35. So 81 times that expression there in parallel with 56k ultimately comes out to be 60 ohms. And because 60 ohms is approximately equal to 50 ohms, I elected just to do away with having a matching transformer and just fed it straight on in. And it's just working fine. That's exactly what we're seeing down here. As we can see here, that's the output of the ADE-1 going straight through that 100 nanofarad capacitor straight into the base of the 2219A. And there goes that 21 to 7 transformer. That's matching, well, right or wrong, it's certainly interfacing the driver with the PA there. Okay, so I think that's all I wanted to cover off from there. So the DC blocking capacitors here are 100 nanofarads, so at the frequency of operation that's a really low impedance, so not having any losses there. That's important. If I didn't have that, then that 0.7 volts there would be shorted to earth. So I need that to fix that, and same with this one here because of the biasing on the base. Right, I think I mentioned before, standard sort of 100 microfarad, 100 nanofarad and 100 microfarads there, just for decoupling, and that is that. So like I say, right or wrong, that's what I elected to do, and as I just said, it's working quite well at 5.6 odd, say again 6 watts or so, so I'm quite happy to leave it at that. The second transistor there is stone cold. The 2219A is certainly not hot. It's it's warm. So I probably might, because I've got a lot of spare space over here, I'll probably elect to put a small heatsink on that. And I'm just debating what I'm going to do with that. Like I say, it's stone cold, so I probably might just leave it as it is, because I'm not into long QSOs, so that shouldn't be an issue. Okay, so I think the plan now will be to transfer this to a proper board and then mount it in the radio. In the past I have used the strip board. I think what I'm going to do this time is I'm going to use some copper board with the Dremel and then just create some large islands and then wire it up sort of dead bug style across the islands, just to get it nice and rigid. So a slightly different approach than what I have done in the past. But it should be good. Certainly I haven't had this take off or anything untoward. Seems to be quite rock solid, so that's good. Quite happy with that. So there you go. It's under ramble now, so I will basically knock it on the head and wish everybody 73, and like I say, build this up, mount it, do some on-ear checks. We can sort of fine tune there that biasing gain from the mic amp. That's absolutely on the minimum there, so I don't need to I don't think I'll be playing around with that anymore. From what I can see on the scope, it's just looking quite nice, so I might just leave that as it is, but that's something I can look at on ear. Okay, 73 all, and I shall see you next time. Cheers all.